Good morning, everybody. Thank you for attending the use of machine learning and artificial intelligence with ArcGIS session. Our speaker today is Yuri Patowski. Yuri is a solution engineer at Esri who focuses on providing local governments the tools and support they need to successfully use GIS technology. His interest lies in the ability of raster and 3D data to model real-world landscapes in an increasingly realistic and representative manner. There's a good number of you guys. If you have questions, please type them up in the chat and I will get them to Yuri at the end of the session. If you are needing education credits, please make sure that you have your correct name, your given name, as your user login. So Richard, I don't know who you are. There was another one. T-Ball, not sure who you are either. Or Freeman U, don't know who that one is either. So if you were expecting education credits, you will not get them unless you put your full name there. The session is being recorded and will be available at the conference website after the event. And with that, Yuri, you're free to take over.
Thanks, John. I appreciate it. And thanks, everybody, for attending this morning and listening to me drone on about GeoAI. And so my plan is to go about between 50 and 60 minutes and then have, some question and answer at the end. So hopefully try to address everyone's questions once I wrap up. But yeah, so I'm a solution engineer at Esri Charlotte, and this is one of the topics that's kind of near and dear to my heart, and mainly because a large portion of it focuses and revolves around imagery, and that's kind of my background. And being able to kind of share any kind of nuggets of information with you all today is I think it's going to be great. So I know that we're all GIS professionals in the IT realm. We've heard about AI a lot. I feel like that's kind of the flavor of not the flavor of the week, it's kind of the flavor of the past 5 years. It's a really big topic. I have a really good buddy that every time I talk to him, he asks me if I'm, are you building Skynet in your basement? And while we're not really going to be building Skynet, we are going to be kind of showing how artificial intelligence can really offload a lot of manual processes that you might be currently doing. And so I hope to kind of pass that knowledge along. So GeoAI, the term is kind of self-explanatory, right? GeoAI is essentially where GIS and geography meets artificial intelligence. And traditionally, these two kind of disciplines have kind of operated in different arenas. Artificial intelligence really started with a lot of complex computing and making a computer aware of what kind of data was getting passed and kind of creating products. Well, recently there was this kind of aha moment where the kind of two have been collaboratively kind of as disciplines working together to kind of create some pretty amazing products. And at the end, I'm going to show kind of one pet project that I have been working on with tree identification, and then two demos that kind of show how AI can really complement the existing work you're doing in GIS. One caveat, I am going to be focusing a lot on imagery. So the large portion of my slide deck and my demos, they revolve around basically image analysis. I am going to talk a little bit about, at the end of the presentation, a little bit about how AI or GeoAI can be used for point features, multi-point features, points, lines, polygons. So it's just because I'm going to harp on the imagery piece does not mean that there's equally as many workflows that you could put to great use, analyzing feature services and feature classes and any kind of real-time streaming data that you might have coming from the field. So it's not a kind of a one-size-fits-all, just keep that in mind. Yeah, so we'll just kind of jump right in. So, why GeoAI and why now? So kind of talked a little bit about how exactly does machine learning complement GIS. So one of the major things in AI is how do we re-envision how existing data that we have, how can it solve new geographic problems or questions? How can it reveal new insights into data? And I'm going to talk a little bit about that and how to get started. And one thing that's really important, this kind of will be kind of a continuous theme throughout my presentation, is AI is now, this technology kind of is found at all levels of the ArcGIS stack. So it's available in ArcGIS Enterprise, it's available with Image Server, it's available in ArcGIS Pro, in ArcGIS Online, and also just on your, with a combination of Pro and Jupyter Notebooks on your desktop machine. And I'm going to try to address all those kind of in turn. I'm going to be focusing mainly on ArcGIS Pro workflows and then a completely Python based workflow. But keep in mind, if you don't have a Python background or this is kind of is newer technology to you, the majority of what I'm going to show today can be done end-to-end in ArcGIS Pro. So keep that in mind. And this third point, I think, is really, really important. This addressing barriers to entry. So whenever I talk to folks, the common is, artificial intelligence, you need this massive computer cluster of GPUs, and you have to pay for all this data, and you need a data scientist on staff, and there's just all these nuances that you have to work through. So I think a lot of users, prospective users, would see that, man, there's a lot of barrier to getting into this field or to getting into this side of GIS. Well, there are a lot of requirements, and yes, it's great if you are doing large processing tasks to have, a ton of NVIDIA, Titan GPUs. That's all great, but the technology can be accessible. All the stuff that I ran today was done on a Dell laptop with a kind of run-of-the-mill NVIDIA GPU. So, and a lot of the tasks can actually be done at the CPU level if they're small enough. So I kind of want to talk about that because I think that that's a real big thing where with kind of emerging technology, people think that it's kind of, this isn't for us. There's no utility for this. What am I going to get out of this process? And so kind of an overview, before we get to this screenshot of Visual Studio and the ArcGIS Python API module, it's kind of important to talk about background and how some of these workflows can be applied within your organization. And kind of as an aside, we have an entire team that works on, AI-based or GeoAI-based projects. So if you have any questions about that in the future, I'll have my contact info on the last slide. Please reach out to me and I can kind of connect you with them. But it's definitely something that Esri has poured a lot of heart, soul, and funds into getting these tools out there. And a lot of these tools are, particularly this notebook, which I'll talk about later here, is completely free. It's on our documentation website. You can pull it down, kind of start plugging and playing with your data and get going today. So I always think it's a great idea to start with kind of a high level overview of kind of artificial intelligence, right? So I'm sure 99% of you all have seen a slide or a graphic very similar to this. It's probably old hat for a lot of folks, and you're probably tired of seeing it. But I think it's really good to kind of start with this kind of opening salvo up front so we can kind of understand kind of the nuts and bolts of what we're trying to do. So as a discipline, artificial intelligence kind of encompasses these other two disciplines. One being machine learning, and kind of a more deeper dive into the machine learning realm with neural networks is what we call deep learning. So I guess a good comparison would be an artificial intelligence example. Clearly, technologies enable computers to mimic intelligence. Well, that's great, but what's kind of a real world example of that? So artificial intelligence, let's say we're looking at an image and there's a bunch of vehicles, right? So an artificial intelligence workflow or model would be able to say, I look at this image, there are a bunch of vehicles in this image. Doesn't know anything about the make, model, color, anything like that. It just understands that in this image, there are 10 vehicles, and it might be able to give you a count, okay? If we go a little bit deeper with like machine learning, let's take that same image, a machine learning model, which traditionally is like one iteration through the data, right? It might be able to say, hey, Yuri, this is a pickup truck. This is a sedan. This is a dump truck, whatever. This is a flatbed tow truck, whatever the situation is. If we go into the deep learning arena, this is where we really get way down into the weeds, and we have all these networks that are connecting and bouncing ideas and extracting edges and doing all kinds of really, really complex stuff. Deep learning models would be able to tell you, this is a gray Honda Civic, this is a white RAV4, on down the line. That dump truck is red, it's manufactured by Ford. So that's kind of the order of operations, or kind of the network depth, right? And what we're going to be focused on today mainly is in the deep learning realm, because that's where a lot of the time and effort and some of the Python, particularly Python workflows, are kind of going in that direction, into the deep learning realm. And this is a quote by Arthur Samuel, who was kind of the godfather of artificial intelligence. And I know that's a lot of text, but the highlighted section is really what I would like, what we want to take away from today is that suppose we arrange for some automatic means of testing the effectiveness of any current weight assignment in terms of actual performance, and provide a mechanism for altering that weight assignment so as to maximize the performance. And so the key terms here are weight and maximize. So you want to have some type of algorithm or some type of model that can learn from itself. And that is essentially what deep learning is. And so I think this graphic does a really good job of showing that, right? So in the top, and I've got a really trivial Python program that I'm going to show in a second that kind of illustrates these models. So a traditional program in the top here takes a set of inputs, runs it through a program, and you get a set of results. So this could be anything you do in the GIS realm, right? I have some point data, I feed it into a GP tool, that's the program. I get a density surface as the results, or I get some type of output tabular data for the results. When I sit down and I write Python, this is how a program behaves. You put inputs in, it runs it through some type of compiler or program, and you get results. So that is the traditional kind of non-nuanced, very basic way that a program works. Well, in artificial intelligence, we're kind of in this second graphic. So we still have inputs, which are your data, your imagery, your points, whatever the case may be. And you actually provide parameters to that, and we call it an architecture. It's a model or a program. It's just a different terminology. You provide those parameters, runs into that model, pops out some predictions at this step. And so these predictions tell you, I think that this pixel on this image is a tree, or I think this is some type of impervious surface, or I think this is a car, whatever the case is. But this is the key step. We have to have data that's labeled, that we know 99.9% with that kind of confidence level. This represents a tree. This represents impervious. This represents a car. And we pass that labeled data into another model, and then we have loss, which is generated. And so that loss represents, we know these predictions and we know these labels, we feed them together, and then we come back out and we update that, and then we kind of do this in an iterative process. So the key takeaways are, you're passing parameters and you have to have labeled data. That's, I think, one common misconception is, oh, you know, AI, just pop in, or excuse me, deep learning, I just pop in some data and it just tells me all this stuff on the fly. And that's not necessarily true. Particularly our tools require you to have training data or data that's labeled so the model understands exactly what the model is looking at. And what we strive to get to in machine learning is this model. We have an input. The model has already done all of this on the back end. It's already been trained to do this. And then we provide some results. And so as GIS professionals, you know, I wouldn't expect any of us to sit around and, you know, do this step, right? We're not creating neural networks. I mean, maybe some of you like to do that in your spare time. You know, that is something that's already done. And so in the ArcGIS piece, we've kind of tried to abstract a lot of that away, right? So you have the model, you decide what model you want to use, and then you feed your data. And it is an iterative process, as I'll show, but it's not as nuanced as this second graphic is. So let me show, and again, this is a very simple program. So in the first section right here, I have, you know, how a normal program would respond. So I have a variable, and what I have here is a list of the days of the week minus Saturday, Sunday. So Monday, Tuesday, Wednesday, Thursday, Friday. Clearly, Friday is spelled incorrectly. But in a normal program, I pass this in. It's very literal. Computers are extremely literal, right? So I would just run this, and we can see in the output, it's still going to misspell Friday, fear day. That is how a traditional model would work, or a traditional program. So this is how an AI or ML or deep learning program would respond. So it knows, because we fed it so much data, it's aware that it's that Monday through Friday, there are 5 days in that list, and that Friday is misspelled. So, and the reason it knows this is, if we go back to the slide, we're constantly feeding data in as an iterative process. It learns, you're confirming that that's correct, and the model learns. So this is where, you know, we get this self-aware term. It's becoming aware of what the data is supposed to be like. And in actuality, a model, an AI model, would also change to reflect the current or the correct spelling. So we can see that Monday, Tuesday, Wednesday, Thursday, Friday are printed correctly in this situation. So this is a really basic, trivial model, but this, I feel like it does a really good way of showing, you know, how a traditional model responds or program responds. And so now, kind of moving on to why machine learning now. I mentioned it's kind of the flavor of a lot of disciplines. I have a lot of friends that are in IT, and every company is doing something in the artificial intelligence or machine learning realm. Really famous quote from another pioneer in ML was George Box, and he says, well, he's actually a statistician, but he said all models are wrong, but some are useful. And so that's something to keep in mind as you work through these workflows. Is all models are wrong, but you can use those to get at some end through interpretation of the data. So why are we talking about machine learning now? There are a few things, at least in my mind or in my opinion, that kind of have led to this huge uptick in this being a really important topic. So the first is copious amounts of big data. I remember as a grad student cycling through Landsat imagery, trying to find a certain panel or a tile that was cloud-free enough that I could do some analysis. And you think of there are I don't know how many hundreds of satellites have been launched since that time, and collecting data, imagery, seconds, minutes, hours. There's tons of data out there, tons of edge devices, right? So a lot of IoT sensors, collecting information about car traffic patterns, speeds, anything you can kind of think of. Rain gauges. There's a lot of sensors that are being deployed kind of into these natural environments to monitor things. So the data is definitely there. It's just, how do we make use of that data, and is that data useful? A lot of it's analysis paralysis, right? We have so much data that we don't even know where to begin, so it just kind of sits unused. And probably the most important, in my mind at least, one of the most important reasons why we're having these really, really robust conversations around machine learning is due to this increased computing power at the GPU level. And so I guess a good analogy, got two good analogies for why using a GPU is important. It's not essential because a lot of the modules, as I mentioned, will work with the CPU, but it is kind of a, if you have a GPU or have the ability to leverage a GPU, it really can make these workflows a lot more accessible. I guess the first analogy I would say is, traditionally, you can think of a drive-through, right? You have the CPU drive-through and the GPU drive-through. When you go to the CPU drive-through, you get to the window and the person says, "Hey, Yuri, sorry, but your food's not ready. Can you just stay put, and it'll be about 5 minutes." Okay, well, while you're sitting there waiting, 50 cars have backed up behind you. Okay, those represent the processes that the machine is trying to achieve at the CPU level. Okay, next door at the GPU level, you pull up to the window, they're like, "Hey, Yuri, your food's not ready. Can you please pull up?" You pull up, those 50 people have already been served and gone through the line. So this is the kind of concept of asynchronous versus synchronous. A CPU works synchronously. You have step one has to be finished before step two can be completed. Whereas with the GPU, you can have asynchronous processes running, right? So you can have 50 tasks running at the same time, and the GPU is really, really good at navigating that and being able to process them all at the same time, or in turn, not in turn, but at the same time. Another analogy I would use is like the CPU is the Lamborghini and the GPU is, the pickup truck. So you've got a bunch of blocks to bring from point A to point B. Yeah, the CPU, the Lamborghini, can put 3 of those blocks in the car and get to point B really, really quickly. But it takes a ton of trips to get back and forth to move all those blocks. Whereas the truck may have to take 2 trips, and it might be slower, but it actually is much better at handling a larger volume. So that's kind of the volume comparison in a more effective manner. So yeah, those are, maybe a little corny, but I think those are a really good way of describing why a GPU is really good at kind of handling these AI tasks. One of the other things, a robust and responsive developer community. Even if you are traditionally just a desktop GIS user, I guarantee you there's a forum, either through the Esri blogs or Stack Exchange or any of these kind of IT-centric websites for posting content. There is somebody else that is trying to do exactly what you're trying to do or trying to achieve. And I've found that when I reach out and talk to these developers or users, they're very responsive. And because a lot of this is, this is you're dipping your toe into the water. This might be the first time you're doing this kind of workflow, but there's a lot of folks out there that are really responsive and helpful. And then probably the most important part of why machine learning is important and deep learning is because of deep neural networks. So up until a couple years ago, or maybe the last 15 to 20 years, these neural networks were here, but there just wasn't the computing power to power those neural networks because they're so input-output heavy. They're always like doing something. They don't sit idle. And there have been just an explosion of the the number of neural networks that have kind of come onto the market or come onto the scene in the recent years. 99% of these are free to use, just like 99% of the environments to run these tasks are free to use on the Python side. So that is one of the pillars, if you will, of why now is the time to kind of be working with machine learning. From an ArcGIS perspective, we offer, and I'll get into this further a little bit later, but from the product standpoint, we provide an end-to-end geospatial artificial intelligence lifecycle. You can see any data that you have, we can ingest stuff from satellites, drones, CCTV feeds, handheld pictures, oriented imagery. If you're just driving down the road and you take a picture of a stop sign, right? We can work with that data. And ArcGIS, in the middle row there, the middle tier, the data access, prep, labeling, training, deploying the models, consuming the models, and then running the inference, that can all be done end-to-end in ArcGIS. So it's not like you kind of have to pick and choose what you're doing with an Esri product. You can literally do all these 7 steps from end to end in ArcGIS. A lot of times with just ArcGIS Pro and the image analyst extension. So, okay, so yeah, Yuri, this all sounds cool, but what can I do? What can my organization do, or how can I leverage this information? So there's been some forthcoming presentations and previous presentations at this conference that really, I think, have hit the nail on the head as far as what can you achieve through these workflows, and what kind of utility can I bring to my organization, no matter how large or small. And so all of this can be done, analyzing traffic accident trends through real-time data and kind of spatial analysis on the back end. Oriented imagery, don't quote me, but I believe that actually this image here is from Charlotte's work with water meter detections. So car drives around, images a scene with a camera. It has a GPS unit in the camera, and it identifies water meters and drops a point at that location. So we see those projects are really successful. We've seen this with road crack detection. We've seen this in this image where this is a case study from out west, the Southwest, where they were just taking handheld oriented images with a camera of exit signs, or there's actually a construction sign to the right, just to the right of that exit sign as well. Capturing that and then kind of wrapping that up into a really awesome operations dashboard, dropping those points, getting quantitative data of those assets in the field. This is extremely, previously this has been a lot of work. Not that it's not a lot of work with these AI workflows, but this helps to streamline the process a lot. I mean, we're talking tons and tons and tons of hours capturing these assets. We can see here, extracting CCTV feeds. This is an example of using a model called RetinaNet. And that just basically creates a bounding box around an image, gives it a unique ID, and then it can count that image if it comes back into the camera feed. It can track that image through multiple camera feeds, and provide you information about, in this case, intersections. I want to say this is Wyoming. I'm not sure. And then one of the latest additions, which I'm actually going to talk about briefly, is the point CNN model for working with Lidar. And so I don't know if anyone attended Dev Summit, or they might have had something as well at UC where they talked about, Dimitri talked about extracting these power line assets and power pole assets with terrestrial, mobile terrestrial Lidar. So that is a really, really exciting advancement, particularly as it's applicable to GIS. So I kind of want to step back a little bit and talk a little bit about what historic AI and ArcGIS has entailed. So I think another common misconception, right, is that AI hasn't been a part of ArcGIS or a part of GIS technology until recently. Well, anytime you've done a supervised or unsupervised classification through image analysis, that could have been in ArcMap 931. That was a form of artificial intelligence. You were passing information into the tool. The tool learned about the data based off of image training data you passed it, and it produced an output. So this is not the deep learning piece is new, but keep in mind there are tons of workflows even still in use today where AI has been a large or comprises a large portion of that data processing. So obviously you would start with input data, raster, imagery, point data, whatever your data input is. You go through some kind of data preparation stage. You process that data. Historically, that was a GP tool. You could think of doing like creating density surfaces with points, and you use the IDW tool to create a raster surface. So that's AI. And then you kind of come to this analysis phase. You're in stage where you're creating land cover maps, rasters, clustering points, or creating segmented data sets. So I just mainly want to portray that it's been an inherent and ingrained part of our software for a very long time. So here are some of those tools. This is image segmentation. This is kind of taking a different approach to creating classifications, right? You're segmenting images into certain objects. And in this image, it's probably very difficult to see, but it's an airport, there's a plane. So those are all segmented into objects. It's not really a pixel level, it is, but it's not a pixel level classification where you're creating containers and dumping all these into containers. So that's been a part of ArcGIS since 10.0. The classification wizard, and in fact, this is a lot of the current workflows you would start with some of the classification tools. And then multidimensional data, you think your net CDF, where you have like temperature, location, and you might have that over a 100-year period, for instance, and kind of clustering. So we can see like this is a covariance assessment based off of some raster data. So I just wanted to mention this because I think it's important that it's not a new topic. It's being talked in a different light, but it's been there for a while. And so these are another 3 examples of some of those ML algorithms in ArcGIS, right? So, I remember doing convolution filtering when I was in school, trying to enhance those edges and just passing a filter over an image, right? And then we have like the iterative self-organizing clustering algorithms for doing, classifications. And so we were kind of clustering those points together and determining an output classified raster, or principal components where we're kind of determining, band A and band B, what's the kind of similarities in those digital numbers between those data sets. So these have been here for a very long time. So the ones that are new, as far as deep learning goes, are, we're doing convolution filtering, right? But we're doing it instead of like just passing a window over an image. We're still doing that, but that filter may run, this is ResNet 34, so it would run over that data 34 times. In actuality, that's not exactly true because it does some skipping around, but there are 34 layers of that filter. And then we have the point CNN classifier in the middle, and we can kind of see for particular Lidar data, where it has an algorithm where it's doing, instead of on the top row, doing that normal convolution, it's doing kind of an X convolution operation. So, and particularly right here, it's measuring and weighting those distances between points. And it learns about that based off of a training data set that you pass it. So this is really exciting, I feel like, in the Lidar realm. And then this is just an output of grabbing some image data and printing out what's on there. So a neural network, right? I think this is the easiest way to describe it. We have a picture of Mr. Washington, and in the first input layer here, we're learning about to identify what are those light and dark pixel values. So this is how the model breaks down the image. Then in the second layer of the network, we're identifying those edges. Then we're identifying a combination of edges, and then we identify features, and then we put all those together in the output layer. And since we've trained on these other precedents, we determine that the output is in fact George. So this is how this is at a really basic kind of limited way of how the neural network works. So it's taking these exact vision principles and applying it to imagery. And so what does deep learning do for us? You know, it can all read this, but basically the summary is you're finding objects in imagery accurately, more quickly, and at scale. Traditionally, the models are so good now that if you can see it as an analyst with your eye or make out what you think it is, and you can train the model, it will perform at or above what we can see. This again, the speed of using GPUs and the scale. So the really cool thing about a lot of these is you can create one model, and you can run that model over multiple images, as long as that imagery is similar in the sensor and the time of capture. You can run this a dozen times to represent 12 time series or 12 years, and kind of do change detection that way. So it doesn't always happen in a vacuum, right? You're being able to reuse these models. And so ArcGIS, as far as the integrated platform, so these are the deep learning packages and the Esri model definition. This is a really cool way to kind of share those models. So if I created a model and I wanted to hand another model off to one of my colleagues, it's all packaged up nice, pretty with a bow on it. I can send that to them, and they can pull that model down and run that on data that they have to see if they get similar results. This again, we've talked about this, GPU. This is a really important part. You can integrate external model frameworks like TensorFlow, PyTorch, and Keras. You create, on the GIS side of things, you would be creating polygon features or classified raster data sets of what those outputs are. Those traditionally fall into a few camps, right? So you're detecting objects, you're classifying those objects, or you're classifying pixels. So I'm going to talk about an image pixel classification workflow shortly. And again, using the whole stack to do that processing. So how do we do this in ArcGIS, right? So this is, I've talked a lot, blowing a lot of hot air about this, but how do we actually do this workflow within the software? So this is exactly how you would do that. The first step would be to create training samples with the label objects for deep learning tool set. So that's not exactly the only way you can do that, and I'm going to walk through that. You can also use classified rasters if you already have them for the training data. You can create, good old feature classes with points, lines, or polygons that represent those profiles or those areas that you're looking for. So if you were looking for a field, you could create a feature class, and it just needs an attribute called class value that correlates to field or whatever that class value is. You export that data with a GP tool, you train the model, and then you take that trained model and you plug it into one of these GP tools that I talked about, one of those three. This is kind of the non-traditional GIS workflow. So this represents a complete workflow end-to-end in ArcGIS Pro, or any image server or enterprise or online. And this represents kind of the non-traditional stepping out of ArcGIS and kind of doing this completely in Python. And I'm going to talk about both of those. So what does this look kind of more visually? Because text on the screen doesn't really do much for me. So we have our images. We label those images. And in this case, we're looking for oil pad wells. We label those. In this case, we just created a feature class of those polygons that represent the spectral values for what an oil pad should be. We've prepped that data, meaning we export the data out, the training data out. We train the model. And this is just the trained deep learning model in Pro. And then we run an inferencing operation. In this case, we're detecting objects because we're wanting to see each one of those individual well pads are like. Then we can do any kind of analysis. It creates, this is an output feature class with the attribution of the digital number values, size, location, all the things that you're used to seeing in vector geometry. It's present here. And you can actually add data, you can do joins, you can do field calculations, whatever you needed to do. You analyze it, and then you might dump this out into a mobile app for inspections of these well pads, right? I might use field maps to go out, have a map, offline map, collect some data in Collector or whatever the case is, and push that back into ArcGIS Online or Enterprise. So these are the things ArcGIS needs. It needs input data from you. It needs to understand what the training or the labeled data are and what model you want or framework you want to use to train that. And kind of the piece of being built to find answers. Information spelled incorrectly, but extracting unseen information, getting derived raster products, these CCTV feeds, and Lidar point cloud scenes. So now I'm going to talk about if you were to sit down at your desk and do this workflow completely in ArcGIS Pro. I am going to step out and show Jupyter Notebook. So because there's about 100 different ways to do these workflows. And so you can do all of it in Pro, but I kind of wanted to show on the back end what was happening in Pro. So first we start with imagery, or in any other case, point data or some type of vector data. You know, how many bands do I need? What's the spectral resolution, spatial resolution? What are the considerations that matter? So I will say that the demos that I'm going to show that I've already done, that was all free data. So it's all freely available to everyone. You can go to the web today, download the same image data that I used, the same models that I used, and run these same tools. So obviously spectral resolution, if you're pulling out images of a specific tree species, right? You're interested in, I don't know, oak, willow oak is yeah, you're interested in that tree example, for instance. Yeah, you're probably going to need, not probably, you will need high resolution data. You're going to need something from a drone that has a high enough resolution to kind of make those assumptions and delineate those tree types. However, I used a 4-band NAPE image that is 60 centimeters, so it's about 2 feet in resolution from 2018, and I got fantastic. Not perfect, but I got pretty fantastic results with using that 4-band NAPE image. And that is by no means a high resolution image. It's not bad, but it's definitely doable. And so those are the kind of considerations. The considerations that matter really are those as to what you're constructing or what you're doing, what phenomena you're trying to extract. Lidar data. The presence of class codes, number of returns, point spacing. These are all important when you're talking about Lidar data. And but the great thing is the North Carolina State data set is fantastic. And you know, that's actually what I trained my model, the model I'm going to show you for point CNN with, and got really, really good results with that as well. So that's something else to keep in mind. So how would that workflow work, right? So I would create the training samples that are representative of the objects of interest. And in this case, I'm creating training samples of forest, and I pass that classification on into the classification manager. And this is the NLCD schema. And I kind of would combine those, and I would get, you know, like 5 output classes. And then I would save this, and then I would export this as deep learning training data. And then this is the label step, right? So we're labeling those objects, and we're creating those training samples, and we're exporting those using the training data for deep learning GP tool. Once we have that data, and the computer knows, the model knows what is it needs to approximate. This represents forest. This represents impervious. You train the model. And you train the model with the deep learning model, trained deep learning model GP tool. So one caveat I do want to say, PyTorch, fantastic Python library, really good speed-wise. It's got a lot of benchmark tests where it's a lot faster than a lot of other modules and frameworks. But this is the only framework you can use to train in ArcGIS Pro currently, or in the platform inside of a user interface. So when you run this model through this GP tool, it uses the PyTorch, what we call a backend. If you are really into this and you want to train, you could train with PyTorch, and then you might want to step out and train with TensorFlow or CMTK or another platform. Then you could do that, and then you use the model here. So I'm going to kind of run through this quickly because I know I'm not taking a lot of time here, but and then there's the completely Python-based workflow, right? This is a little nuanced. You know, when I first started using this kind of data, you know, I felt a lot like this. You know, I was kind of overwhelmed. How do I start? What do I do? And because there are all these frameworks here to kind of use. And I would encourage you just to experiment with Pro and use PyTorch, and then once you kind of have a comfort level there, then you can kind of move on to one of these if you want to. And then you would use Jupyter Notebook, which is, if you're not familiar, this is basically a runtime for parsing code. It's kind of a compiler for running Python code. But what's really awesome about Jupyter Notebooks is you can see here, you can create these incredible graphics, just like charts, graphics. It's very much like a website that you can save these. You can provide these as notebooks to other users to be just uploaded into ArcGIS or whatever, you know, whatever flavor of software you're using. And it's just a really awesome open source platform for creating these tools and running these tools. You know, unfortunately, you have to step through these kind of running these, installing these libraries and these modules, which can be a little nuanced, but this is straight from the documentation where you can run these series of commands, and there's a workflow exactly laid out in our documentation on how to install those. But these tools are very literal. If you don't have every environment specified at the correct version and the data isn't exactly what the tool is looking for, it will not work. So just be very aware of that you know, it's whatever the GP says it requires, the GP tool is going to require that. And I think this is my last, this is the last slide, and then I'm going to jump to the demos. But so notebooks, ArcGIS Notebooks is basically our version of Jupyter Notebook that is integrated into the software. So Jupyter Notebooks is completely open source, and you could go to the Jupyter website, you know, and today download and start running and working with some of these models. So they are integrated in every level of the platform. In Portal, there's a notebook server option that's an add-on, but that you can run notebooks. They're in ArcGIS Online now and in ArcGIS Pro. And I actually ran a lot of this stuff just off of a local installation on my laptop here at home. Same workflow for training outside with a different framework. You have to label those objects, you have to train the model, and then you kind of deploy and use the model. So this was the first kind of side pet project I was working on that I just wanted to kind of show. And if you saw at UC, there was something a lot better where Madeline gave used survey 123 for taking an image of some type of a plant in the field and running a TensorFlow library on your you know your Android or iOS device, and it would add up in real time, identify what that tree was or what that plant was. So that's really cool stuff. A lot of work is being done in that realm for offloading these processes to mobile phones or tablets. But this is just something that I did. I was out, took some photos, you know, took some photos of tree leaves. I pulled out all the image information, and then I ran the geotagged photos to points to create points of those. And then I fed a ResNet model or ImageNet model of these tree leaves, and wanted to see if it would correctly identify those trees. And around 78% of the time, it was correct in identifying what those tree species were. So, and then I created an Excel document and joined those back together. So now when I click on those points, I have the tree, and I identify that tree roughly 78% of the time based off of the leaf appearance. Okay, cool. So I'm going to jump into showing you some of these workflows. So this is ArcGIS Pro, obviously, and this is Lenore, North Carolina, right here, and one of my favorite places in the world, High Brine Mountain. And this is just a 4-band run-of-the-mill nape image. And, you know, as I mentioned, this is meters, so it's about a 2-foot resolution, freely available. And what I did was I created this training data with 6 classes. And as we can see, some of these classes, like these for field, these are pretty much home runs, right? They're clear, there's really no shadows. These are good to go. But some of these, like this polygon that I created, is supposed to represent deciduous trees. And then I had a class for evergreen for predominantly pine species. But you can see that these really aren't completely leafed out. There's some deciduous trees in here that still are not leafed out, or leaves have already dropped. It's not as far as land cover classification, this image is not ideal, right? And we've got all these shadows on the backside, on the north side of this mountain where this cliff is. And there's shadows everywhere at this quarry. So not real great for, at least in my mind, for doing an image classification. But I was blown away by the results I got. So I created this training data, and I fed it, I think it was, so for buildings, I only fed it 11 records. So for those urban areas, there's a high school here, you know, 6 of these or 5 of these came from these 2 buildings. So there's not a lot of variance, right? I didn't spend a whole lot of time on, you know, my polygons are kind of sloppy. They're overhanging some of the urban area or the building area. I didn't really spend a whole lot of time, because I just wanted to see mainly what the model could do. And I created this, and there are kind of a couple workflows that you could do. You could create the training data like this, or as I mentioned before, you could use some of the classification tools. And so what I did was I created this training data, and then I essentially passed it directly to the model. But what you can do is you can use the training samples manager to create those, and then you would label those objects for deep learning. And so that workflow essentially does exactly what the training samples manager does. You label your objects, create a schema, and then you export the training data, and this fires off the GP tool. Didn't do that. And then I trained this model. I actually trained this model in Pro, and then ran the output. I kind of wanted to show that in Jupyter Notebooks, so you kind of have an understanding of what I was doing. This is simply the path to the output training data. So when you run the export training data model, you get these series of folders. You get some image chips, which are TIFF images, and then you get labeled imagery. So this is the imagery that I labeled with those training samples. And so if we look closely, I just path to that. I prepared that data, and you can pass it a nape parameter because that's what I was using. And I see I have my 6 classes, and then I wanted to just show the information. So this is a perfect example, this right here. we can see that I labeled some of this in the lower image. So it's going to grab this and use this as one of the image training chips, or one of the image training images rather. I used UNet, I did the fit, and I fired off the model. And by the 20th epoch, that's just run through the model 20 times. Each epoch is a run through the model. I was achieving 99.9% accuracy. And don't want to go down the wormhole on these two things, training loss and validation loss, but traditionally you want them both to decline. If the validation loss becomes larger, if this number was larger than my training loss, that usually points that the model is overfitting, it's becoming too smart, and it's classifying things incorrectly. You kind of have that law of diminishing returns, right? Once you hit the peak, you got to stop there. And I created this output raster, and I'll kind of show that to you. Now, this model is not perfect by any means, and there was some kind of superpixel growth, but we can see that it did a pretty good job. And we can look back kind of just visually at the NAPE image, and it classified all this as building. Now, and it even captured these series of field houses here, which to me, you know, and then we've got some mixed pixel issues in here. This should actually be classified as grass or open ground, and it classified that. It actually did, it grabbed it. So this was with only like 45 training labels. I mean, this was blowing my mind. I didn't spend any, it took me like 10 minutes to grab those training samples. I didn't provide any, I didn't fine tune anything on the model side. I ran this completely in Pro with the defaults. And I mean, to me, I mean, this output is, you know, is spectacular. I mean, we even got some, if we look where I tried to do kind of the division between deciduous and evergreen, I mean, we can see that there's some, I would assume these are like pine species. It grabbed those pretty well. So, and this was like, the model took about 15 minutes to train. So start to finish, this probably took 25 minutes completely. And you can only imagine what the output would be if I had really spent time on that training data and kind of attributed it more correctly. So to me, this was, you know, insane results given the data, and plus this NAPE image is not great at all. So I thought those results were really good. And the other thing I wanted to kind of show was some Lidar data. And so I have, this is Hickory, North Carolina. This is the hospital. And I have some Lidar data that came from the state data set. And basically what I did was, it's classified, and I just assigned everything that was not low, medium, or high vegetation. I unassigned it. So I gave it an assignment of 1 in the ASPRS classification. So this is a good data set. We can see visually. I mean, it missed some things, but pretty spot on. Like particularly for these trees, this is awesome. This quality of this LiDAR is awesome. And what I did is if I step back to Jupyter Notebooks, I trained this model with just like 13 lines of code, not even, because I've got spaces, and got some phenomenal results with that too. The unfortunate thing about LiDAR data and the point CNN classifiers, you cannot currently make use of this in Pro. You have to do all the training and the exporting from Jupyter Notebooks. You can't train the model currently. You could do it through Jupyter Notebooks and ArcGis Pro, but I mean a geoprocessing workflow. So then let me step back into, I have this data for Davidson, North Carolina, and I wanted to compare. I was like, you know, Hickory, Davidson, fairly urban areas, and then I have this Davidson unclassed data set. I was like, I'm kind of interested in what's, you know, if I train off of the Hickory data or the data that was captured for Hickory, can I get a pretty good output for a similar environment at Davidson? And so I did that, and this is kind of the workflow that I used. And if you have any questions after about these notebooks, or you want to talk about this, I'm happy to talk about. I'd love to have a conversation around these. Some of these are on my GitHub page, so I'll kind of post that at the end. But basically, you export the point data set here from this is the Hickory class data set, and it gives you a series of output data sets in this location. And what's funny about this is I didn't provide any validation set for this, and that's like a new total. You would never do that. You have to have a validation set for the model to train against. But I just ran it to see if it could train without having the validation set. This took a while. This was 5 epochs. I mean, this last run took 5 hours and 54 minutes. So this takes some time, but the output was, again, I thought really, really great. So if I zoom to the Davidson. So this was the 5 epoch data set where I ran it 5 times. And we can see that a lot of these trees that are high vegetation actually came back as low vegetation. So it did a really good job of pulling out and training on vegetation, right? But it didn't do a very good job of classifying those into the correct division. So what I did was I reran that model with 20 epochs, and this was the output I got. So we can see that high vegetation, we're getting great results off of this high vegetation. In the low vegetation, we can see, I mean, it's incredible that I trained this off of a different data set, and I'm getting this kind of results on a different area. So let's see if, I mean, even these trees here, we're getting really good return values off of, and I would say the classification is pretty good for the Davidson data set. And I did this for trees as well, in like a in an environment where there was a lot more tree cover, vegetation, and not as great results. But I think the thing to take away from this is this would be really a great way to train for asset extraction, right? So grabbing building footprints, grabbing, railway infrastructure, grabbing these kind of power lines that are strung here between these poles. So I think that's a really good, that would be my takeaway would be, you can, while mine was kind of a trivial classification, you can easily kind of replicate this for classifying stuff that you need to extract. And that's kind of what the point CNN classifier is good at. So that's all I had. I know that was a lot. Went really quickly through that, but one thing I did want to show really quickly, and then I will, is this is not isolated to just raster data. So I wanted to show there's a lot of data models that we have that you can train for tabular data. So if you're working with feature classes or web services, you can kind of plug and play what's called a fully connected network and the ML models to work on tabular data. And that's a lot of the work on crime that I was showing, traffic patterns, all of that is done off of tabular vector data. And if it has an attribute table, these models will work with that. We have an example of predicting forest fires if it was caused by arson based off of variables. So you can kind of imagine what you could use that for. And I would point out, we have in the Arcgis API for Python where all this comes from or starts, there's a ton of information on doing these workflows. There's a ton of notebooks. Literally a couple of the notebooks I took were straight from this repository. There's I think 50 total. So, and anything you can think of, there's probably an example that you can adapt to for your use case. So with that, that's all I had. Then if there are any questions.
Sorry.
I don't know if you're on mute, John, or.
John is on mute. So, John, okay.
There we
you
go.
Got it?
Well, I was just talking, so I thought I unmuted myself. It took me 1 minute to find it, and then whatever. Technology, right? User error. So there are a number of questions, a couple anyway. The first one is a 3-part question, and they want to know what percentage of efforts has to be taken to train machine in a project generally? How much model data needs to be used to train the machine? And what is the size of a project, acre, square miles, urban, rural, to use AI to be efficient?
Yeah, so I think to all those questions, it's I hate to say this, but it depends a lot on, great questions, by the way. It depends a lot on the like the resolution. If you're using high resolution imagery, that processing time increases exponentially. So for example, the NAPE image that I used, pretty small. I don't know how many acres that would be, but maybe 25,000. That took, like I said, less than 20 minutes. So in that respect, it can be quick, but the thing to keep in mind is that I didn't really hyper parameterize the model. I didn't really feed it really great training data. So that is all, that's all the stuff that's really, really important. The cool thing is if you have an image from, let's say that was Caldwell County, where I'm from. So if you had that whole image of Caldwell County, and my suggestion would be test that set on a really small, you could even do a much smaller area than I did. You could do maybe 5,000 rows by 5,000 columns in a raster data set. Train it if you're comfortable with that. You can actually use that model that you've created really quickly, probably within less than an hour, to train on the larger data set. Particularly the pixel classification, and that's what that is. They're not particularly taxing, but they can take some time. The Lidar data on the other end is just, it's a monster. So it took I think like 22 hours to train the 20 epoch run. So I would start small and then extrapolate from there. I don't know if that's a great answer, but and I would definitely look for data that was much better, obviously, than mine. That was not a great image, and I think that the model had some trouble, like shadows, kind of identifying those shadows. But I'm happy to talk offline about that if you start down that path and you want to kick some ideas around on that. I'm happy to talk about that.
The next couple of questions are about Notebook. Is it possible to use Notebook without using ArcGIS Pro license? And is it possible to use the Notebook's AI capabilities with Portal 6 or 10.6.1, or does it have to be 10.7 or later?
I think Notebook server was 10.7 or later. I'd have to verify, but so a few things. You don't have to have an ArcGIS Pro license to use Jupyter Notebook. In fact, I just installed Jupyter Notebook, and you can download actually the ArcGIS API module to Jupyter as a Python module, and you can call those tools. That would require a license for like image analyst, but to just use general Jupyter Notebook, like if you're consuming freely available web services that are on ArcGIS Online, no, you don't have to consume a license. If you use it in ArcGIS Online and it is usable in Portal, yeah, that's a license. And actually in the enterprise environment, it's a server role, actually. So you have to install ArcGIS Notebook server as a server role to kind of do that processing. But no, Jupyter Notebooks are open source. It's open source software.
Okay. Are any or many people using phone photo apps like Diopetra with phone GPS and phone direction info to input image and data automatically into their GIS databases?
So I don't know exactly what platform they're using, but we do see there is a large uptick in this kind of what that would be, considered like oriented imagery, right? And actually the tree identification that I did, that was all done for my Android with location services, and it was surprisingly effective. But I don't know an exact answer to that question. But there are definitely, that is a really big topic, at least internally at Esri, about how you handle that oriented imagery. And we actually have an extension, so I would encourage you to check that out on the solutions site for handling oriented imagery. And there are a number of workflows in the Python API for working with oriented imagery. But as far as like uploading them automatically, I'm not positive.
You mentioned neural networks were free to use. Where do you find these networks and how do we access them?
Yeah, so a lot of these are from academics that are, incredibly sharp in their disciplines. And a lot of them, like ResNet is one that's really, really well known and very widely used. Was the result, I believe, of a Harvard research paper. And so in the case that I was in, all the examples I did, those neural networks are already, those models are already kind of baked into the software. So if I, let me see if I can pull one really quickly. 1 second. So for instance, if the ArcGIS Learn module is where all of those models are, we can see that like for point CNN, that's the model, and you would call this class to run that model. So in that respect, a lot of these are already baked into the software. Like the UNet classifier, this is what I use to train the land cover data. It's already there for you. You just use it. If you're not really, you're not pumped about the results that you got, what you can do is you would have to do that through Python. You unfortunately can't do that through Pro currently. You would just have to use Python to point to a library where that deep learning module or that deep learning neural network is. A lot of times you can download those. Like when you download PyTorch or a framework like that, they come with a ton of those models, many more than are available in our API. So they're already kind of pre-cooked for you. It's just kind of connecting that dot and finding it and using it. So I would check the PyTorch models, the TensorFlow models, and kind of start there because they have a ton that you can use.
Okay, and I assume there are tutorials available from Esri?
There are. Yeah, exactly. What I would start with is actually this one. Let me see if I can. There's a really awesome, this one. So on the learn.arcgis.com site, there is this this step-by-step workflow on how you use deep learning to assess these palm trees. And it walks you through from step A to step Z. And even in this, it's optional to have a machine with a GPU. You can run all this with a CPU. But it walks you through the whole process of the training samples, detecting the palm trees, downloading data, and estimating health. And literally every single deep learning workflow you do in GIS is going to follow this process. Training samples, exporting those, training the model, and then creating an output. So I think this is a really awesome start. I would also check out some of the previous technical presentations and user presentations for that matter at some of the user conferences, or particularly Dev Summit from this year. They gave some really fantastic presentations on deep learning. And You know, when I started, there was not a whole lot of documentation, and it was just kind of a learn as you go. The really great thing about this AI world is there's a lot of practitioners outside of GIS that have posted a lot of content online. So, but this is a good place to start. And also I would definitely start with those sample notebooks that I showed before.
Awesome. Thank you very much, Yuri. I hope everybody got some really useful information out of that. I know I did. You should see a poll. If you would please fill that out. And I hope you enjoy the rest of the conference today. Thank you.
Thanks, everyone.